Hello everyone, welcome back to Physical Geology 1403. It's week 3. We're starting lecture 5 today. You are 25% of the way through my class. It's flying by. Time flies when we're having fun, huh? Right? It's going too fast. How are we feeling?
Pretty good.
Pretty good? Good? I'm hearing good, pretty good. Anyone feeling bad? Anyone feeling uncertain? Anyone feeling like they still don't quite get the concept of the class or where you are in it? And it's totally okay. Please raise your hand. I can't address a problem like that unless I know there is a problem, right? You don't have to be self-conscious about it. You're probably not alone if that's how you feel. And if that's the case, then I need to change the way I'm delivering the class, okay? Yeah.
I'm so stuck on lab 1 for tenacity.
Tenacity, yeah.
Tenacity.
Is that the last thing you have to work on?
And the name.
And the name. Okay, well, that's not bad. Who else is still on lab 1? All right, that's most of the class, right? You're not alone. Thank you for bringing that concern up. I guarantee a lot of my online students would have raised their hands if they were here physically as well. They may have done it just now in their living rooms or wherever they're watching, right? Like I mentioned before, it's totally fine if assignments take a little while longer. Just remember, try not to make that a habit. It's, lab 1, I get it. You're still figuring out how to do labs in my class, and it's the longest lab. So yeah, if you need another week on it, sure, that's fine. But lab 2 is half the size, and you already know how labs work, so you definitely don't want to take 2 weeks on that one. And you definitely then don't want to take 2 weeks on lab 3, because guess what? All of a sudden, we're out of semester, and you still have 2 labs to do. Okay? So you don't want it to snowball is what I'm saying. But it's perfectly appropriate for y'all to still be finishing up lab 1. Let's try and get that done today, though, so that we don't experience that snowball. Okay? But as far as you're concerned about tenacity, would you like me to explain it real quick? Great. Tenacity is how a sample breaks. Okay, so where cleavage describes the planes along which it breaks, if it has planes of cleavage, tenacity is more along the lines of its appearance as it breaks. For example, brittle tenacity means that it shatters. I hit it with a hammer, it breaks into a bunch of little shattered pieces. Okay, please don't actually hit my samples with hammers. You are looking at how they are already broken. Okay. And then there's malleable as another example, kind of like Play-Doh, where if you exert pressure on it, it'll bend into the shape that the pressure forced it into and retain that shape. Then there's elastic, where if I put some stress on it, it will bend, but as soon as I release that stress, boing, it goes back to the original shape like a rubber band. Okay? These are examples of tenacity, and you have all of them as on the Lab 1 PowerPoint. There's a spreadsheet, or not a spreadsheet, excuse me, a slide that has all of the possible tenacities and their descriptions on there, okay? So you're more or less just describing the way that the mineral looks like it was broken. In a full spectrum test, yeah, you would break it to see. But I'm not in a department made of money, so I can't constantly be replacing my samples like that. All right, does that help? Awesome, thank you for bringing that up. Hopefully that helps y'all finish up that lab today as well. Any other questions? Any concerns? Y'all refreshed after your holiday, that 3-day weekend? I mean, let's be real. Fridays are half days, right? Was it kind of like a 3.5-day weekend? Kinda? Any of you get any work done over the holiday? I didn't. It felt good. Okay. Shall we begin, or are there any burning questions? Any interesting stories? Any interesting facts that you heard? Huh? What was that? Oh, you were telling him something. Oh, okay. You don't want to share it. Fine. That's fine. I'll just keep going. All right. Then let's begin. Today we're talking about weathering and soil. We left off talking about the igneous and volcanic processes, right? Magma forms rock. Well, the next part of that rock cycle that we talked about is that rock breaks down. That process of breaking down, we have a word for that. Weathering. Okay? Someone remind me what the word dynamic means again. Huh?
Movement.
Movement, that's part of it. Dynamic, anyone? Yeah.
The deposit.
That's part of it. Dynamic as a whole. The word dynamic, what does it mean?
Two things supposed to be together or something like that?
No, we're touching on tiny little components of what dynamic means, but I'm looking for the whole. What the word itself means, not just elements of it as it manifests on Earth.
Something that energizes.
That's also a component of the word dynamic. The word dynamic means characterized by constant change or activity. And everything that y'all just gave me, all these elements, are examples of change and activity, motion, deposition, all of that stuff. These are things we'll talk about today, but they are tiny little elements of what the word dynamic itself actually means. We already learned about how Earth is dynamic, right? Can anyone give me a few more examples? Earth is dynamic how? The way it's built. So the processes that make the things that we see. Yes, exactly. Okay. So we get all of these different processes that occur in the world around us. We're going to talk about a few more of those processes today. But we've already learned that it is through these processes over time that we see things happen, right? A few examples here. The growth of a plant. How many of you have tried watching grass grow? How fun was that?
Boring.
It was pretty boring, huh? You didn't see much. But what about over the course of a week? How much do you see? Yeah, you see okay, out here it might be a bad example. But if you lived in a place, I don't know, like Seattle, Washington, right? Imagine how much your grass grows there. Right. There are some places in the world where the grasses grow extremely fast. There's a species of bamboo, by the way. Bamboo is, in fact, a type of grass, if any of you didn't know that, as is rice. Okay, rice is also grass. But there's a species of bamboo that can grow a foot in 24 hours. You literally can watch that grass grow. But for the most part, yeah, you don't really see much. It takes the process plus time to see any sort of change. So this is a very slow aspect of how dynamic Earth is, but still an example. As a matter of fact, most of these processes take long amounts of time. Someone remind me how old the Earth is?
5 billion years old.
A little less than 5 billion, yeah? Yeah, it's about 4.543 billion as far as we are aware, okay? Close to 4.6. Okay? The sun's about 5 billion years old. Okay? Our star. Okay, so all of there have been processes occurring on Earth for that long. Not the same processes, but processes still. And a lot of those processes are still ongoing. Some inside of the Earth and some on the outside. We get the most experience with the ones on the outside. Okay? Some other processes that take time. Rust. Rust is an example of this process, right? What is rust? What is the process of rusting? Do you know what that is?
Carbon. The metal reacting to carbon.
It's not the metal reacting to carbon. The metal is reacting to something. Not hydrogen. Do you know what the actual terminology for rust is, what we commonly refer to rust as? It'll be a dead giveaway when I say it.
Weathered metal.
Weathering is something I'm going to bring up here in a second. The actual, yeah, what? Yeah. There's an important thing on the end of that, and that's the result. The rust itself is ferrous oxide. The process is oxidization. Thank you. Yeah, slow oxidization. The iron combining with oxygens, commonly oxygens that are dissolved in water, making ferrous oxide. And it puts that brown stuff on the outside. That's actually iron that is oxidizing. Fun fact, fire itself is a form of oxidization. It is rapid oxidization. You apply enough heat, all of a sudden you start an oxidization process.
So once it starts, it doesn't stop until you like.
The rusting? Yeah, you have to remove it from that environment and take all of the loose oxygens away from the equation, which is why it can be hard to reclaim certain metals once they've started to rust. That's why it eats its way through. Okay? Some metals can be reclaimed. If you get to it early enough, you can clean the outer surface. Often it requires grinding the outer surface of metal off so that you can take off those loose oxygens. And then if you're wise, you put a sort of lacquer or some sort of sealant on the metal to keep it from rusting again. And there are some alloys of metal that you can actually make that do not rust at all. They do not have an open chemical slot, so to speak, for the oxygen to attach to. We've learned how to do all of this, but these are kind of besides the point. You get the idea of rust and how it is an aspect of dynamic, right? The term dynamic. Well, it's also an aspect of weathering. What is weathering? Weathering is the breakdown of something, okay? Weathering is the process by which things are broken down, rust being an example. What about the decay of plants? Yes, this is an example as well. Plants fall apart. Tree dies, falls down. Over the course of a decade, it molds and rots away. That's an aspect of weathering. Well, what about weathering as it relates to rocks? That's also what happens. The term, or the actual definition for weathering is the response of a material to a new environmental parameters. And how do things typically break down when you put them in a new environment? Or how do things typically respond? I guess I just gave it to you. They break down, right? Things respond commonly by breaking down. There's a mineral I told you about before called olivine. Do you remember where olivine typically forms? Huh? No. Well, we get a lot of it in ocean rock because the ocean rock is primarily mafic, but olivine itself primarily forms in the mantle. There's a lot of olivines in the mantle. Olivine forms at high temperatures and high pressures. So why don't we have more of it at the surface if so much of the mantle is made out of it? What do you suppose happens to that olivine when it gets up here? It breaks down. Why?
It's a new environment.
It is, and that means what? Not enough heat and? What's the other thing? Your mouth wants to say it. I see your pressure. There it is, okay? I can see you making that P, right? Okay. So, there's not enough heat and there's not enough pressure up here at the surface. It's not the same environment that that mineral formed in, and therefore, under a response to new environmental parameters, what's it going to do? Break down. And so that's why we don't have a whole lot up here, even though so much of the mass of our planet has that chemical composition. Okay? So, let's talk about this. These are external processes, okay? The things we're talking about today. Weathering, erosion, mass wasting, okay? These are all external processes. What does that mean? They happen on the outside of our planet. This means that they get their power from the sun. Their energy for these processes is derived from the sun, okay? So as this radiation makes its way through our atmosphere, hits our surface, it does things. It warms up certain parts of the surface and not others. What does that do? It creates an unequal distribution of air pressure. Do you know what happens when you get an unequal distribution of air temperature and therefore pressure? More basic than that, actually, before we even get there. Wind. Wind is the product of unequal air pressure, okay? Often caused by temperature changes, okay? Which side of the planet is the sun on? Is the sun shining on ocean or is it shining on land? Okay? These will affect that. Then you've got your things like your currents. Okay? Your ocean currents. Those are also reliant upon temperature. And you know where that heat comes from? The sun. Okay? Often at the equator. All of these are powered by energy from the sun. And so weathering and erosion and mass wasting, the things we're talking about today, get their energy from that. Okay? So the first one, weathering, that's your physical breakdown of your material. Well, I shouldn't say physical. It's just the breakdown of material. Physical is one aspect of that. Okay? But like this is kind of an example of artificial weathering here, but you get the idea. It's breaking down this material. Okay? Then you've got your, we'll do this one first. They're out of order. Okay, but you've got your transport, your erosion. Erosion is the transport of broken down material. You'll find that some people, actually most people, if I'm being honest, confuse these two words. Weathering and erosion are two separate concepts. Weathering is the breakdown. Erosion is the transport. So if you hear someone say, oh my goodness, look at all the erosion that's happened on this mountain, what they actually mean is, look at the weathering. It's been breaking down, okay? Look at this rock. Look how smooth it is. It's been eroded into the shape. No, it's been weathered into that shape. Erosion is the transport of the stuff that got weathered off of it, okay? So remember that terminology here. Then you've got your mass wasting, and I'll just play this other one again here. What is mass wasting? Mass wasting is the movement of material driven primarily by gravity. It's a little bit different from traditional erosion for reasons we will talk about later on in the class, okay? But mass wasting, where gravity is the driving force here, that's a separate subject that we'll get into later, okay? So, there are two types of weathering. The first one is mechanical weathering. Mechanical weathering is the physical breakdown of a material, just like with that jackhammer or with any other hammer. If I were to break something down, that would be an example of mechanical weathering. A rock falls and hits another rock and they break into smaller pieces. Physical weathering. A river is running over the same stone for 100 years and smooths it out. Mechanical weathering. Okay? And I'll go over some other examples here in a minute. But what happens here is you get a chunk of rock and it slowly starts to break down, piece by piece by piece by piece. Here's an interesting thing. The more pieces that breaks down into, the faster the rate of mechanical weathering increases. The faster it gets. Why would having smaller pieces mean more weathering, faster weathering?
Because it's easier to break down.
Because it's easier to what?
To break down?
To break down. Why is it easier to break down? Say it louder, I'm sorry.
Because it's smaller.
Because it's smaller? Is it easier to break down just because it's smaller?
It's faster to break down.
Why is it faster to break down, though? That's the question. Why is it breaking down faster? If I have one big block of rock here, and it takes 100 years to weather it down into these smaller pieces, why does it only take 50 years to weather these into these smaller pieces?
Because it's not as much mass.
It's the same amount of mass, because we're just breaking this piece into smaller pieces. Mass stays constant in this example. Huh? The bonds? There are bonds breaking here, but that's not why. Good thought, though. Yeah. It is. It is the surface area. With this first big block here, if we assume that each side is 2 units, we have 2 by 2. That's 6 sides of 4 square units each. That's 24 square units. We take that same mass and reduce it down into smaller blocks of 1 unit per side. Count up the total amount of surface area. All of a sudden, we have 48 square units. Do that again. Reduce each one of these into smaller blocks of 1/2 by 1/2 sides of units. Okay, and we get 96 square units. The more surface area you have, that's more surface area that's exposed to the changing environment that it's going to weather in response to. So as you reduce your rock into smaller and smaller pieces, the rate of weathering increases because the amount of surface area increases. You following along with that? Great. Another phenomenon that we will often see is rounding of these rocks, of these blocks. Have you ever picked up like a river stone and it's nice and smooth and shiny and pleasant to hold? You like maybe to skip it on the river or lake or whatever. But the point is it's nice and round and smooth. Why? Why does water do that? Maybe you've seen wind do that too. Why does that phenomenon occur?
Water like seeps through the bonds and breaks the weak ones.
Okay, so you're thinking about something called chemical weathering, and don't worry, we're going to get to that next. This is an aspect of mechanical weathering occurring here. Why would it make a nice, smooth shape? Where's my block? There it is.
You said, why would it make a nice smooth?
Yeah, why would we get a river stone when you put a rock in a river for 100 years? Why does it round it out?
Because the water's hitting it and it's also hitting other rocks.
It's removed. Okay, so that rock is bouncing against other rocks. Sure, the water is constantly moving against that rock. That's the action. That's the application of energy. Why the result is that smooth shape is because corners have more surface area. Yeah, I've got it on the slide. Okay? Corners have more surface area, and therefore, where is the fastest rate of weathering going to occur on this shape? The corners. If I weathered away the corners of this block in enough time, I would have a sphere. If I have a rectangular shape, I weather away the corners. Given enough time, I'll have an oval. Right? So that's why we get rounded stones with the application of water or wind energy given enough time. It takes away the corners, rounds them out until you end up with a much smoother shape. Some other examples of mechanical weathering: frost wedging. When I have an environment where water seeps into, say, a cliffside, something that looks like this. Water seeps its way into the cracks in this rock. Come winter, next time it freezes, what's that water going to do?
Turn to ice.
It's going to turn to ice. Fun fact, do you know that when water turns into ice, it swells, it increases its volume? That's why ice floats in your drink. It's still water. If your drink is water and you put ice in it, ice will still float. Why? Because it has increased its volume by about 9%. Not much, just enough to still float in liquid water, though. Okay? The bonds making solid water have arranged themselves into a network that takes up more space than liquid water does, and therefore density decreases. So the volume increases, it swells, and as that water, which has made its way into the cracks, increases in size, it pushes the cracks a little bit wider. Every year, every freeze, thaw, freeze, thaw, freeze, thaw, freeze, thaw, it pushes that crack wider and wider and wider until finally stuff falls off. That's mechanical weathering. That is frost wedging. Okay? Then you've got salt crystals, which kind of work in a similar way. Whenever you have water near a body of rock, salt water I should say, and the salt water kind of laps up onto that rock over and over and over, as it leaves a little layer of water on that rock, that water evaporates pretty quickly and leaves behind the salt, because salt can't evaporate with the water. The salt crystals start to grow inside of the little nooks and crannies in that rock. And as that salt crystal grows, it starts to push out little flecks of rock. Pushes them out, kind of same way that the ice did in the last example. And so you get these pockets in your rock where the salt crystals have pushed out little pieces of rock over all that time. Okay? Salt crystals. Also, this is the reason why we get so many potholes in our road during the winter. What do we put down on the road when it gets icy?
So,
Salt. Where's that salt going to go? Into the cracks in the road. Every time that water evaporates away, those salt crystals, they grow and they grow and they grow and they push the cracks in our road wider. And then the more traffic that those roads see, and then more ice, and then more salt, and then more salt crystals, and you end up with terrible, terrible potholes. Which is why most cities in the northern states and in Canada don't even use salt on their roads. And salt will dissolve the ice, sure, because salt water has a lower lower freezing point, right? You can freeze it, but it takes a lot more cold, and it needs to be a lot colder, okay? And then the salts also won't be in that water, okay? We'll talk about that another time. They use, bless you, instead of melting the ice, bless you again, they use sand or volcanic ash for friction on the roads. They just dump it on top of the ice on the road, and your tires just have better traction. Doesn't sound quite as safe, but it saves millions and millions of dollars in road construction, right? And if you know what you're doing driving on ice, it can still be really safe. Okay? Sheeting. This is in Yosemite. Okay, it's a national park. I highly recommend. It's beautiful. But what you're looking at here is a granite dome. This is an igneous intrusion. Okay, so it's made out of granite. It used to be a magma chamber. Exposed now at the surface. Under what conditions did this granite form? Underground, from magma. What conditions were present there?
Heat and pressure.
A lot more heat and pressure than we have at the surface. So how's it going to respond up here?
It's going to break down.
It's going to break down. It's going to experience weathering. How? Through sheeting. Okay, so what you're looking at here, do you see how it's kind of breaking off in layers? There's no layers in this granite. It wasn't deposited in layers. It was one big unit of granite. So why is it breaking apart in these layers? This is called, another word for this is exfoliation. The outermost layers of this dome are breaking off in kind of like shells off of the interior. And then those are going to break off, okay? So essentially it's cracking off in kind of eggshells. Imagine if you cracked an egg and you took off all of the outer shell and inside there was another shell. And then you took that off and inside there was another shell, okay? Shell by shell, it's going to crack off sections off of this dome and it's going to fall off the side. We call that sheeting or exfoliation. And then there's biological activity. A tree. Look at this tree. Its roots have grown into the crack of this rock. As that tree root grows, it's going to push that crack wider and wider, ever so slowly, but still going to do it. Until eventually that whole section right here is going to fall off this cliff because that tree grew so big, it forced that crack so wide, the rock couldn't hold on anymore. Gravity wins, okay? Gravity always wins. Okay? Any questions about mechanical weathering? No? Well, now let's talk about chemical weathering. Okay? That's the second aspect of weathering. Where mechanical weathering is that physical breakdown, chemical weathering takes place at the atomic level. The bonds, the dissolution of those bonds. Okay? So, most commonly, chemical weathering happens with exposure to dissolved elements in water. That makes sense, right? Water falls as rain, right? The ocean, rivers, lakes, all of these have water in them, and all of them have something dissolved in that water for the most part, okay? So oxygen dissolved in water is going to, say, rust metal. Carbon dioxide dissolved in water is going to make carbonic acid. Sulfur dioxide dissolved in water is going to make sulfuric acid. You get the idea, okay? So in what circumstances do these happen? Well, oxygen dissolved in water happens literally all the time We have a lot of oxygen in our atmosphere. Carbon dioxide dissolved in water. Do you think that's pretty common? Do we have a lot of carbon dioxide in our atmosphere?
Yes.
Yes, we do. Ever more of it. All the time, becoming more of it. So yes, more and more often, carbon dioxide dissolved in rainwater is common. Okay? Sulfur dioxide, this is much less common. Sulfur dioxide in the atmosphere is usually associated with areas that have lots of volcanic activity or lots of factories. Okay? Lots of manufacturing byproducts, or sulfur dioxide is the byproduct of a lot of manufacturing processes. So in places that have a lot of like smog, where you can look at the city and there's just like a haze over the city, like San Francisco or Salt Lake City or a whole bunch of other cities around the world, that smog, like London, it only gets worse and worse and worse. Okay? Sulfur dioxide is one of these gases that's a problem with that. Now, when any of these gases dissolves into water, it makes a light acid. Have you ever heard the term acid rain? Yeah? When I say acid rain, you all immediately probably thought of like it's falling from the sky and stuff is melting, right? It's like that's how the movies like to show acid rain. There isn't actually any acid that can form in our atmosphere like that. Okay? Sulfuric acid is pretty harsh on, say, plant life, and I sure wouldn't want a sulfuric acid rain on my car or in my yard. It'll kill all my grass, right? And it has a negative effect on a lot of minerals, which we'll talk about here in a minute. But the stuff like that'll melt anything, that's called molecular acid, and you don't like that doesn't fall out of our atmosphere. Okay? Far more common than sulfuric acid, though. Yes.
What about the red one? The red rain that fell in India, I believe.
The red rain that fell in India.
I believe it's India.
When was this?
1896, I believe.
1896. Well, that long ago, the account may have been changed. It may not be reliable, but even if it was, I will say that some crazy things have fallen out of the sky. There have been fish that fall out of the sky hundreds of miles inland. And why? Because they got picked up into the atmosphere by a big old water tornado and carried inland before they fell.
Didn't Peter like rain frogs or something like that?
I think you're considering the plagues of Egypt is what you might be thinking about there.
Rain frogs.
You think it rained frogs here?
Like little baby frogs.
Little baby frogs. Oh, that makes it way more believable. I have not heard about this. If this is like a local legend, I haven't heard of it. Okay. However, red rain may be the product of something similar to the fish thing, where an algae bloom could have gotten picked up into the sky and dropped like that. It's possible. I have never heard of the red rain that you're talking about, though. I can't think of anything that would form in the atmosphere other than dust that could color rain red naturally.
It's like almost this color red.
Interesting. Yeah, I've never heard of it.
I don't know if you can see it from here.
How do they have a picture of it from 1896?
I don't know. It just says it's from 1896. I think it has done it several times.
Interesting. Yeah, I've never heard of that phenomena. I would say it has something to do with dust pollution or potentially maybe even red algae that got pulled up into the atmosphere and then rained down somewhere else. But I'd have to know more about it before I could make any solid assessment of that. For the most part, though, the most common thing that we get is carbonic acid. Because we have so much carbon dioxide in our atmosphere and ever more, okay, we always have more going up into the atmosphere, so carbonic acid is becoming more and more common. This carbonic acid interacts with minerals, and for some of them, most of them actually, given enough time, it will break them down. For example, here, I have, it's probably hard for you to tell, but if you're following along on the PowerPoint, you can see this, the mineral calcite. We're all familiar with calcite at this point, right? Yeah? It's on your lab. Hint, hint, if you haven't found it yet. Okay? Calcite, CaCO3. 1 calcium, 1 carbon, 3 oxygens. CaCO3 plus carbonic acid equals a calcium ion and a bicarbonate ion. What does that mean? The carbonic acid will break my calcite down into two smaller units. The calcium ion, which will just kind of flow away in the water, get utilized by something somewhere else, and the bicarbonate. What is that bicarbonate? Have you ever filled your glass with water, drunk most of it, and then left it on your counter overnight, and you come back and the water's dissolved, like evaporated away, but it left a white powder in your glass? Very common around here. We get that white powder a lot. If you have reverse osmosis or a water softener, you might not see it as much. Okay? But here, who here likes drinking Odessa water? I've never met anyone that does. I'm not terribly fond of a water you can chew. So, yeah, it's pretty chewy water in here. Hello! How are you? Okay. Oh, what do we got? Oh, yeah, thank you. Okay. This is cool. This is the first time anyone's ever actually bothered to give me one of these. I don't know what to do with it. Do I leave it here? Do I give it to someone? I don't know what to do with my hands. I'll have to figure it out later. All right. Okay, so we're talking about chemical weathering. Carbonic acid, very common, breaks stuff down. We just talked about how it breaks down calcite. Okay? And you get those bicarbonates and calciums. Okay? So it doesn't only do this to calcite. It does it very easily to calcite, but it doesn't only do it to calcite. Most other minerals will respond this way given enough time. For example, what do we have in a granite? Most common ingredients in granites that we'll find, potassium feldspar. Okay? So, potassium feldspar, we have potassium, aluminum, silicon, oxygens. It's a silicate. It's built around a silicon tetrahedron, right? So, we get our silicon, or our potassium feldspars, plus our carbonic acid, plus the water that carbonic acid is inside of. And what does that balance out to? We get this big old long thing, Al2, Si2, O5, OH4, plus, that's a clay, by the way. We'll get back to that in a minute. And then potassiums, and then bicarbonates, which we already talked about, and then silicas, loose silica ions. Okay? So it turns out feldspar also breaks down in the presence of carbonic acid, just a lot slower than our calcite does. It will, however, eventually. So what is this showing us? There are things in our water that break down minerals chemically. Okay? It's not harmful to you and me under normal circumstances, but it will break down those minerals. As this water is flowing through the ground, which it does in this process called groundwater, which I'll teach you about in a little bit, this groundwater will dissolve the rock that it goes through. As that rainwater falls from the sky, it will dissolve the minerals that it falls on, ever so slowly, a little bit at a time. Okay? Now let's talk about the ingredients here, the results of this. Remember, feldspar is the most common type of mineral we have on our planet, on our surface anyway, right? About 50% of our surface we estimate is feldspar of one kind or another. So it breaks down into clays. Clays form the backbone of our soils, which we'll get to in the other part of today's lecture. These potassiums are gobbled up greedily by the next living thing that can find them. A plant, an animal. We all require potassium to live. Okay? And so those potassiums are often taken up pretty quickly. Bicarbonates stay in our water and make that nasty dust at the bottom of our glass, but they also get utilized by animals out in the ocean to make their shells. Okay? And then silica. Where do our silicas go? What happens to them? these tiny little microscopic, chemically produced silica ions flowing through the water. Any ideas? Well, what happens is they encounter something. Sometimes it's a void in the rock, like a hole in the rock. Sometimes it's a fossil. Sometimes it's a piece of gravel that got stuck in another bit of rock. Whatever the case may be, they encounter something. Often it'll be those voids. And they will start forming layers of solid silica on the outside of these voids. And then another layer on top of that, and another layer on top of that, building from the outside of the void in as the water is flowing through this system. And this, my friends, is how you form agates and geodes. It's through those chemical weathering produced silica ions from the breakdown of silicates that get carried through the groundwater and make these. You've seen these before, right? You've seen a nice agate before. You have one? Yeah, well, now you know how they form. Okay. So, here we go. Some of the most common silicates that we see on our planet. Quartz will chemically weather down into silica. No surprise, it's only made out of silica. It's SiO2. That's all it's got. Okay? Then you've got feldspars. They will break down into clay minerals with loose silicas, potassiums, sodiums, and calciums, depending on the type of feldspar in question. Okay? Then you've got amphiboles, which break down into clay minerals. And then, because these are dark silicates, aka ferromagnesian minerals, they also make iron oxides, limonite and hematite, with a few silicas, calciums, and magnesium ions off to the side there as byproducts. Then we've got olivine. Olivine only breaks down into those iron oxides with some silica and magnesium left over. So, knowing what we know about the ocean crust, knowing what we know about the formation of ocean islands, and knowing what we know about chemical weathering, explain to me why Hawaii has red soil. I want you to chew on that for a second. Before I...
Amounts of minerals?
Different amounts of the minerals.
Like, already said that.
This is what I like to call a logic train, where I take multiple ideas of what you've learned in the class so far, pose a problem, and ask you to explain that problem using several different ideas of what you've already learned. So let's start at the top. Tell me how Hawaii formed. Who wants to start there? Jackson, you had your hand up. Go for it.
Volcano erupting and the lava coming over the lava pillow coming up and it.
Lava pillow, that doesn't sound very pleasant to lie down on. I know you're talking about pillow lavas. I'm just poking. Okay, but what kind of lava? Anyone want to help him out? Huh? Well, it's at the surface, so it's lava now. Mafic. Yes, it is mafic composition. Lava. Good. We're putting this together. We're going to do it together. Did you have something to add? No? Okay, so mafic, lava at the surface. That's a lot of stickers. I want to look at those later. Okay, so mafic lava. What's the next step? It cools off and makes what? Mafic rock. What's the ingredient? What's the chemical composition of mafic? What does that mean? I'm me start calling on some other folks.
Like the dark silica?
Yes, it's going to be made out of dark silicates. What does that mean?
Oh, it's gonna be.
They're all based around a silicon tetrahedron. That's what makes them silicates. Emily, any ideas? None? Do you remember what the other name for dark silicates was? Starts with ferro. Remember that one? Anyone want to help out? I already gave you half the word. Ferro magnesium, which means it's made out of what?
Magnesium.
Magnesium and no. Anyone over here? What does the ferro part of ferromagnesium mean? There are two elements that are in high quantity in those minerals. Anik? Iron, yes. Iron and magnesium rich minerals. Ferromagnesium, also called dark silicates. This is what mafic minerals are made out of. Okay? Come on, camera. Stay with me here. Hello? Why are you having a hard time? Look at me. Hold, please. What's the deal? There we go. Okay. Hello? There we go. All right, so we've got an island now made out of mafic rock, which is rich in ferromagnesian minerals. What do those ferromagnesian minerals break down into? Faith, any ideas? What those ferromagnesian minerals, which include these, what do they break down into? It's okay to read off the slide. They're right there.
Silicates?
Well, they are silicates to start off with, but they break down into what? Right here. We definitely have clays. Yes, that's essential for soil. So we're getting closer to the question, to answer the question here. But they also break into what? Can you read what those are? This is limonite and hematite. Do you remember what I told you those are? Those are iron oxides. So we have clays and iron oxides coming from the breakdown of this mafic igneous rock, which is basalt, by the way. And it makes, what color is iron oxide? It's red and brown, isn't it? Rust. Yeah, iron oxide, rust. Already talked about that today. Red and brown. So why is Hawaii's soil red, my friends? Because of the breakdown of the iron and magnesium-rich minerals in the mafic igneous rock that made the island. You just connected 3 different ideas from 3 different lectures to answer that one question. This offhanded question that someone might ask, maybe you're just having brunch with some friends one day, and you're like, you know what's been on my mind lately? Why is Hawaii a red dirt? You know the answer, right? That'll come up one day. I'm sure it will. But you get the idea. This is how you answer scientific questions. You connect these different ideas together, okay? At no point have I ever had a lecture entirely about Hawaii and its dirt, but now you can answer a question based off of 3 different concepts that you learned from 3 different lectures in the class. Okay? That's the logic train, and this is going to come up every now and then. I'm going to pose a question to you, and you're going to use a logic train as a class to figure it out. Okay? Great! Now, another byproduct of chemical weathering is spheroidal weathering, which is a tough word to say. Spheroidal. Okay? Yeah, you can try saying it if you want. Spheroidal. Okay, so what happens here is this is very similar to what you were bringing up earlier, by the way. You've got a layer of rock, and your water kind of seeps down into it, and it starts having a chemical reaction with your water. It makes it start to bubble up. Okay, some minerals, some layers of rock will respond to water by swelling. Okay, they will suck in that water. There'll be some chemical reaction, and it'll swell up as a result. And so you get this sort of bubbly effect on the surface of your rock. Kind of looks like blisters. Okay, that's called spheroidal weathering. Any questions about chemical weathering? Or about weathering at all? Okay, let's talk about weathering rates then. You've already learned that all minerals have properties. Yes, you may. Yeah. You've already learned that all minerals have properties. Okay. You also learned that all minerals have melting points and therefore cooling points as well, right? That's what Bowen's reaction series was talking about. You remember the M&M's exercise we did? Okay. They have melting points, they have cooling points, and all these other properties. It should not be that weird a concept to think that they also weather at different rates. Namely, if a mineral is harder, it's probably more difficult to break. If a mineral does not react to acid very strongly, it will weather slower than the ones that do, right? These all add up to weathering rates, and there are some characteristics that dictate that. The type of mineral we're talking about to begin with, right? What is it made out of? How soluble is it? That is, how easily does it dissolve? Okay. Let me give you another example here to help you understand the whole physical rate here. Okay. So if I had you ever seen the sugar cubes? Like what you put in tea and stuff, right? If I put a sugar cube in a cup of a hot beverage of your choice and I stirred it, it would take a little while for that sugar cube to dissolve, right? But if I put a teaspoon of sugar in there and stirred it up, it would dissolve almost immediately, right? Different rates of solubility based on, in this case, surface area. You remember we talked about that? The larger surface area is actually in the teaspoon of loose sugar than it is in the cube. The cube is bigger, sure, but has less exposed surface area and therefore takes longer to dissolve. So that's just an example of how different things weather at different rates based upon their characteristics. Okay? So, and then there are some external things that can dictate that. Climate, for example. Temperature and moisture. If I have more rainfall, my minerals are going to be exposed to more potential acid. Less rainfall, less exposure to potential acid. Okay, so in a place like, I'll use Seattle, Washington again, where it rains 320 days out of the year. There's only about 40 to 45 days where it doesn't rain typically in a typical year in Seattle. Okay, any of you ever been? You better have a good rain jacket if you go visit. I love Seattle. I miss the rain. Versus here, where we might get 20 or 30 days of rain a year on a good year, right? If it's anything like the years we've had lately, we'll get 5 or 6 big storms that last a day or two, and then that's it, right? The rest of the years is dry. So our minerals here get less exposure to that acid in the rainfall. So what's the effect of this? Look at these two gravestones and tell me which one is older. There. Clearly, this one is the oldest. Why?
Because there's a bunch of holes in it, like indents in it.
Yeah, it kind of looks like crap. It's been broken down, right? It's fallen to pieces, whereas this one is not. Actually, this one is older. This is the older gravestone. This is the younger gravestone. So then why does that one look like this?
Because it was made of different, like legal material.
Ah, it is indeed. This one is made out of marble. This one's made out of good old granite. Marble is made out of the mineral calcite. And we all know how easily calcite falls apart, right? It's very soft, and it dissolves in pretty much any acid you could put it in. You dump carbonic acid on a marble gravestone consistently, and yeah, it's going to start dissolving away. Whereas granite, sure, it's going to dissolve a little bit, but not nearly at the same rate because it's made out of different stuff. Okay? Nothing that dissolves quite as easily as calcite. Look at that. Not only do you know how to pick the perfect countertop, you also know how to pick the perfect gravestone. My class is so practical. All right? Okay. Any questions about weathering or weathering rates before we move on to our discussion about soils? Yeah, sure. Anyone? Alrighty then. What is soil? Someone tell me what soil is.
Soil is something you put in the ground to have something.
It's something we put on the ground?
No, it's like dirt. And a bunch of
It's like dirt?
bunch of like minerals,
Ground up minerals?
like salt.
Is that all it is?
Nah, there's rock in it, right?
Well, rocks are made out of minerals, right? So you're both essentially saying the same thing, but is that all it really is? Is that all soil needs? If all soil needed was ground up rock, then why aren't we living in a rainforest out here in West Texas? Ah, there must be more to it. Water. Good, that's an example. Let's talk about this. So, soil. If my PowerPoint would like to catch up. No, don't you do this to me. It gave me the Microsoft PowerPoint is not responding pop-up. Ah, here we go. It caught up. All right. So, soil is actually a lot more than just dirt. Soil is something that is essential to our biosphere. We could not live on this planet without soil. What grows in soil? Plants, yes. And what does everything in our planet require to eat? Plants at some point or another. Can you look at any part of the food chain and not see plants in it somewhere? Right? No, we need plants. We need plants. How many of you had a hamburger over the weekend? Wow, not that many barbecues, huh? Okay, well, I had a hamburger over the weekend. You know what that cow ate? Plants, I hope. It ate plants, right? That's what was advertised, anyway. How many of you like salad? You do not want to see me eat a salad.
Why not?
My wife says it's something like if you put a fox in a bucket with a bunch of baby chickens. Yes, I dig into that salad with gusto, let's say. Okay, I am a salad fiend. I absolutely adore salads. Okay, I like eating plants. I don't even need to eat the thing that eats the plants. I am the thing that eats the plants. At some point, plants are essential to the food system, to our food cycle, to our food web, no matter how you look at it, and they need soil. So this is something that's actually pretty important for us to understand. The concept of soil and how to maintain it and how to make it. You mentioned that it's something that we put on the ground. We can, but most of it's already there, right? Let's talk about this. Soil is not just loose rock or sand or dirt, okay? It's a combination of 4 different things. You've got your mineral ingredients, your water, your air, and your organic ingredients, okay? Your organic part. Yes, the organic component is called humus. And I put this up there because it is humus, not hummus. It's not a delicious Middle Eastern dish made out of ground chickpeas. It is humus, okay? That's how you say that. Humus is the organic component, the decaying plants and animals that get incorporated and worked into the soil over time, okay? And this is a very important, very delicate balance because your soil for a particular region is not the same as the soil anywhere else. It has been adapted to that region, and the plants have to adapt to that soil. In general, you'll see a very small amount of organic content compared to a much larger amount of mineral content, and then some variation between air and water. These two will go back and forth. depending on where we are. Do you think that our soil here has more water or more air?
Air, actually.
Yeah, more air, right? Do you think that the soil in the Amazon rainforest has more water or more air? More water. Do we have the same kind of plants that live here? No. Very, very different biota. Okay? Primarily because of the difference in soils, which is caused by the change in environment. Let's talk about this. That the process of forming soil begins with the breakdown of your mineral content. You do need that mineral content in your soil. Okay? So, we have two different types of soils depending on the origin of our mineral content. Let's use this river valley as an example. If my mineral content for my soil comes from a local body of rock, we call that a residual soil. Okay? So if, say, this rock right here weathered away and the material eroded down into this valley and the soil here is made from the rock from this hillside, then yeah, we'll call that a residual soil because it's made from that bedrock that's right there. But if the soil in this area is made from mineral content that got washed downstream for who knows how many miles and stopped here and made that soil, we call that a transported soil. Not because the soil itself was moved there, but because the mineral content came from somewhere else. And how do we know that? We just look at the chemistry of the soil. If the mineral content does not match the minerals in the local area, we know it came from somewhere else. Okay? Now, naturally, time is a big component in this too, because what did we just talk about happens more and more over time. What's going to continue to happen to that soil, to the mineral components in that soil over time? It's going to keep breaking down. Weathering does not stop, right? It's going to keep breaking down. And as it does, it's going to slowly resemble less and less what its original parent rock would have looked like, chemically speaking. Okay? Why? Well, plants are pulling things out of the soil. Okay? They're utilizing the loose potassiums and calciums and nitrogens and oxygens and all of those things. The silicons are getting pulled up. The potassiums are going downstream. The bicarbonates are moving along. The chemistry of our soil changes constantly given enough time. It's harder to tell where it came from. Okay? Some other things that help dictate soil, the climate. We just talked about this, the difference between the Amazon and here, right? Very different soils. I'll actually go into the different kinds of soils that we have in the Amazon here in a minute. But the climate is the biggest factor. How much water is available and how much organic content is available. Okay? That biological input is very important. We don't have the same biological input to our soils here as people in the rainforest do, or as soils in the rainforest do. We don't have even the same amount as people just a little further north do. Okay? The grasslands up north get more biological input than we do in our soils here. Okay? The type of organic input as well is important. Pine forests. If you go up north, actually if you go west as well, you'll run into pine forests. But if you go up north, you get some really big pine forests. Okay? Pine forests tend to inhabit the higher altitude areas. So the further up north you get, the more of them you will see. Okay? They have developed this fascinating evolutionary advantage over time. And I'm going to dive a little bit into evolution here for a second, just for a minute, because it's so cool. Okay? You'll get your fill of this in 1404, believe me. But here's just a snippet. Okay? Pine trees have developed an ability to have an organic acid in their pine needles. There is an acid that when their pine needles fall to the forest floor and start to decay, it generates this organic acid that seeps into the soils. When you go walking through a pine forest, you don't really see much other than pines. Every now and then you'll see a weird bush or a stunted tree of another kind, but for the most part, all you're seeing are pine trees. Any of you guys ever walked through a pine forest? No? None of you? Yeah, you have? Can you affirm what I'm talking about? Can you remember seeing... Yeah, really big trees, but is there much else other than pines? No. And here's why. That organic acid basically burns away anything else that tries to grow there. Any tender little tree seed or bush or anything that tries to grow in that soil filled with this organic acid cannot survive. It's a huge advantage that pine trees developed as a method of self-preservation. More resources for my species, not yours. Pine forests are essentially just pines. So bearing that in mind, when you want to grow a crop in a place that once was or still is inhabited by a pine forest, you got to take that into account. When my parents moved to North Idaho 11 years ago, they bought 11 acres in the middle of a pine forest. Okay? My mom wanted to plant an orchard. She tried planting some pears and some apples, and they died pretty quick, and she could not figure out why. Then she did an acid test on her soil, and lo and behold, yes, it was rich in acid, this organic acid. It was killing her trees before they could grow. So she had to treat that soil. A very common method to treat this, you neutralize that acid with something that will essentially absorb the acidity. Okay? Crushed limestone is an example. Why? Well, because it's made out of calcite, and the acid will dissolve calcite, and they'll neutralize each other. Okay? So you mix crushed limestone in there or some other acid neutralizer, and then she has a flourishing vineyard, not vineyard, but orchard now. She's got some nice pears that come in. Okay? I think she even has some apricots now, if I'm remembering right. Okay? She grows blueberries and all of that other stuff. It just took a while to treat the soil for it. So this is an example of how the organic input can affect your soils. The microorganisms as well. What bacteria are in your soil that are breaking down that humus and making it acceptable for use in the soil that other plants can use? Yes. Okay. Topography is another factor here. Topography is the elevation change that you observe in your area. Okay. Your whole Lab 5 actually is going to be about reading topographic maps. So don't wait. You're going to have fun with it. Okay? Just you wait. But right now, I'll just say that topography is a description of the elevation profile of your area. So what does that mean? How high up above sea level am I? Also, what direction is my slope facing? Is it facing the sun or is it facing away from the sun? How successful are my plants going to be based upon the sun's direction? If you go walking through a forest, especially in a wetter part of the country, I'll use Seattle as an example again, then you'll often see that moss is growing only on one side of the trees. Why? Why do you suppose that is?
Soil on the other side,
For one reason or another, the sun most commonly shines on that side of the tree. Therefore, that's the side that the moss will survive on the best. Same thing with hillside slopes. If there's one side of your hillside that gets more sun and one side that does not, guess what? You're going to get more stuff growing on the side with the most sun. Okay? The angle of my slope is important as well. If I have an angle that is too steep, what's going to happen to my water?
go down.
Yeah, it's going to start running all the way down. I'm not going to retain much, and it's probably going to carry my soil away with it. What happens if my angle is too gentle? That's how we get bogs and marshes. Okay? When you have a very flat or no slope at all, the water just stays. It saturates the soil. It gets boggy. It gets muddy. It's not really successful for a healthy soil. Okay? So these are all factors that go into making good soils. And the wide variety of soils that we have around the world. By the way, we have a lot. I'll show you in a minute. So when you go digging down through your soils, you're going to notice that there are some color changes that you observe. And some of the layers are going to be thinner and some of the layers are going to be thicker depending on where you are and what soils you're looking at. But in general, these are your soil layers or horizons. Okay? You have your O horizon, which is primarily organic content. your decaying leaves, your sticks, your dead squirrels, stuff like that. Okay? Then you've got your A horizon. Your A is going to be that really nice prime topsoil. That's what you like to grow your stuff in. Okay? The earthworms live in that. Your animals burrow into that. Your tree roots stay in there for the most part. Okay? Then you've got your E horizon. Okay? The E horizon is the zone of eluviation or leaching. Okay? It's usually a very pale color because a lot of the good stuff has kind of been pulled out of it. Okay? What you've really got left there are some older clays, bicarbonates, stuff that plants don't really use, and so it just kind of hangs out at the bottom. Then you've got your B horizon, which is where you get packed clays that have fallen down from up above. Okay? They tend to get condensed and pressed together. And then you've got your C horizon, which is just the breaking down, the actively breaking down bedrock underneath of that. Okay? Now, in a place like the rainforest, your O horizon is going to be a lot thicker because there's a lot of stuff that's constantly living and dying in a rainforest. In a place like here, we basically have no A horizon. If you were to go walk outside of town, anywhere that doesn't have a manicured yard, and dig in the soil, there would be an extremely thin or non-existent A horizon or O horizon. Okay? Not a whole lot of organic stuff on the surface here. So all of these different variations add up to a lot. Okay? So there are 12 different orders of soil, which I have given to you here, just for curiosity's sake. This isn't going to be on an exam or anything, okay, these names. But there are 19,000 different series of soils within these 12 designations. And guess what? That's just how we classify them in America. There is no universal soil classification, at least none that I know of. Pretty much every major entity in the world has their own classification method. But that's a lot of different types of soils. So I'm going to pose a question to you. Why does clearing the rainforest hurt soil? Why is it bad for the soils over there for us to clear the rainforest? We can all agree that clearing rainforest is bad, right? Is anyone here pro clearing rainforest? No shame if you are, just curious. Okay, well then we can all agree that it's not a good thing. Why is it not a good thing?
Because it destroys habitats for animals there.
Sure, it destroys tons of habitats. What else?
Where oxygen comes from that.
We're killing trees and we get our oxygen from trees.
Because the trees cover the soil.
Trees cover the soil. Let's dive into that a little bit more.
They, like, without the trees, the rain can go, like, take those nutrients away from the soil.
Ah. Without the trees, the rain can take nutrients from the soil. Rain, as it turns out, is not that discerning. It doesn't just take away the nutrients from the soil. It takes away the soil. Yeah, here, let me show you real quick. If I were to jump onto good old Google here and say Amazon River Delta. I'll teach you what a delta is in a bit, but I want to show you this picture. What's the first thing you notice about that river? It's brown, isn't it? Why is it brown? It's full of soil. It's full of soil from all the places that are getting cleared of rainforest. And every time it rains, there's nothing to hold that soil down. That soil gets washed into the nearest tributary. What are the kind of favors do you think that's doing for the ecosystem in that river? If we lived in a constant windstorm full of sand, Like we couldn't even see 10 feet in front of us. We just lived in a constant dust storm. How great would our environment be? How great would our breathing quality be? No, we'd all have asthma. It would be terrible, right? That's basically what all of the fish and other animals in this river have to deal with. It's all just dirty now. Not from anything bad, mind you. It's not pollutant in the terms of like plastic or anything like that. It's soil. But that's soil that's not meant to be in the river, at least not in this quantity. And you know where it goes, by the way? Let's see if I can find one that shows the ocean. Yeah, here we go. Here's a wider view, a larger satellite view. High def image, it'll take a second to load. Okay, so here you can see a much larger section of coastline. Where is all of that soil going? Out into the ocean. Before, we were only looking at this, guys. Now we're looking at the actual ocean out here. Look at all that soil that's getting washed down to the ocean and carried out to sea. Deposited off the coast. Never to be utilized again by anything living on land. What a waste, right? Now, when you clear away the rainforest, you're removing those roots that hold the soil together on the surface. Really quick, notice how thin the layers on top of this clay soil here are. The O and the A together are relatively thick, but the roots for these trees don't go down into this. Look how thin the layer that holds the roots for these trees are. The trees basically only live in the O and the A horizon in the rainforest. They hardly even go down into the mineral-rich section. In the rainforest, the plants live and die so quickly, they don't develop deep root systems. Really what they're doing is recycling the same nutrients from plants to plants without really getting much new nutrients from deeper down in the ground. So you clear away that top section with all the plants, and all of that unutilized clay can get washed away downstream. This is the city Angkor Wat, by the way. It's in Thailand. It's really old. I want to say it's like 800 years old, something like that. It's made out of bricks from these clays. That's why they share the same color there. Makes for a very hard, very dense brick. Very difficult to break, which is why that city has lasted so long. Okay, soil erosion is something that is becoming a worse and worse problem. Okay, used to be that only a few billion tons were washed out to sea every year, and now it's significantly higher than that. I want to say the last estimate was, gosh, maybe 90 billion tons of soil is washed out to sea every year because of the amount of forest cutting that's happened. There's nothing to hold it down anymore. It's pretty bad. What are we going to do without any soils? Let's assume that soil gets washed out to sea enough that all of a sudden we don't have enough for our needs. Camera, stay with me. Come on now. Hello. You're doing it again. Don't be weird. Come on. There we go. Okay. Let's assume that a lot more soil gets washed out to the sea to the point where we can't use it. What happens? No crops. No food. We've actually gone through this. You ever heard of the Dust Bowl? I'm glad they still teach that in school. Okay, the Dust Bowl happened in the 1930s. Okay, this was an event where the United States suffered two events. A bad drought, so the soil was already pretty dry in the first place, and also a lot of over-farming. We didn't quite know how to take care of our soils as well back then. Okay, And so after decades and decades and decades of over-farming, plus this drought, a huge part, hundreds of millions of acres of the American West and Midwest, dried off so much that all of the soils started getting blown away. And there were incredibly massive dust storms. They buried entire communities. They buried cars on the road. It was extremely dangerous to try and cross this area at that time. Okay? This guy is standing where the current ground level is, and his arm is at where the ground level was before the Dust Bowl. That's how much soil got blown away from this part of the country. A huge part of the country. Okay? Hundreds of millions of acres. Now, we've recovered from that. We've reclaimed a lot of that area, but not nearly all of it. A lot of it is still unfarmable because of the conditions that still continue. Okay? A lot of it is not recovered. So, but this was something that we could learn from. A tough lesson because it led to some famine, but a lesson nonetheless that we can learn from about how to better take care of our soils. Okay? So what are some things that we can do to take care of our soils? It was 24 billion, by the way. I think I said 90 something. It's 24 billion tons of soil is washed into the ocean every year now. So what does this water, or what does this soil pollution do to water? Okay. Well, first of all, it'll cloud it up. But think about the things that get washed into that water with the soil. We use these things called insecticides, right? Insecticides in our soils to kill insects and things that like to eat our crops. Those insecticides are poisons. Do you want to be drinking insecticides in your water? No, neither do the fish. Okay? What about fertilizers? Well, fertilizers are good, right? They help our crops grow. Isn't that good? Do you know how they help our crops grow? They use things called nitrates. Nitrates are great for growing crops, but it also turns out they're great for growing algae. Nitrates get washed in with our soil into the water, and you get algae blooms in your lakes, in your reservoirs, in your rivers. That chokes out all the rest of the life, kills off that ecosystem. What about just the soil itself? If I have a lake or a reservoir next to a dam, and that lake or that reservoir next to the dam starts filling up with soil at the bottom, where is the water on top of it going to go? If I have a cup that's half filled with water, and I dump sand in, where's the water going to go? It's going to get displaced upward until eventually what happens?
It goes out the cup.
It floods out the cup. And that's exactly what happens to lakes and reservoirs if you fill the bottom with sediment. They overflow out. And guess what? There's usually communities next to these things. So there are a lot of effects as a result of soil erosion that people don't really generally think about, but have to be considered because they're important to us and our world. Okay? So now let's talk about some ways that we can mitigate these effects. Terracing. It's growing more and more common for farmers that have hills on their property to utilize those. Well, what do? They essentially build steps into these hills. Because as the rain is falling and as it's carrying soil away, as it's eroding soil away, it'll get eroded from up here, down here to this step. It'll get stuck there for a while. They can grow with it. Then eventually it might get washed down to that step. And then they can grow with it again. And so they can preserve the life of that soil in this area for a lot longer by essentially building these steps that soil has to get through to eventually leave. Then there's windbreaks. Have you ever driven along a farm and there's a line of trees between the road and the farm along the edge of the property? Those are called windbreaks. They're usually some sort of tree that you can also, make money off of, maybe pecans or apples or something like that. But their main purpose is to cut the energy of the wind before they reach the actual farm. It reduces the amount of dust that is removed from or blown into your property, so you can maintain your soils. Then there's crop rotation. Crop rotation is essentially, this is something that we owe our founding fathers, by the way. George Washington, Thomas Jefferson, they all experimented with stuff like this, where you divide your property into different sections and you grow different crops based upon a rotation. So for example, in spring, I could grow crop 1 here and here, and crop 2 here and here. And then in fall, when I want to do my second harvest, I could have 1 and 1 here and 2 and 2 here. Now, why does that make a difference? Because you choose which crops you put there. So instead of just doing these this year and those next year and these the year after that and those the year after that, you can continue using all your property, but with complementary crops. For example, corn and beans. Corn puts a lot of nitrogen into the soil as a byproduct of its growth. Beans pull a lot of nitrogen out of the soil as a byproduct of its growth. They complement each other. So I can do corn, beans, corn, beans, corn, beans all year round without exhausting my soil. This is crop rotation. Responsible use of soils while also maintaining a product that people can use. Any questions about that? Yes. Yes, you may. Let me ask you another question. Why do we strip the rainforest? Backing up a little bit there. But why do we strip the rainforest of trees? For wood to build things. I wish that were true. I wish that we used all that wood. A lot of it doesn't get used. Yeah.
To not like have like big disasters with forest fires.
Okay, so you're looking at it from the perspective of you have to clear some of it so that you don't get bad forest fires. That can be true in some parts of the world. And as a matter of fact, here in the United States, every now and then they will do a controlled burn to prevent a potential big disaster forest fire in the future. However, in the rainforest, that's not so much a problem. Juliet, any ideas? Why do we clear the rainforest? To develop like communities? Is that what you're thinking? That's a good thought. And to be fair, some of that does happen. New communities do pop up in the rainforest, but not enough to account for all the clear cutting. So that's a contribution, but not the main factor. Any other ideas?
Factories,
Factories? What do you mean?
like they can build factories.
Oh, for industrial development. There's probably some of that as well, but along the same lines as the communities, right? Not nearly enough to account for all of it. The number one reason why we clear cut the rainforests is for this. This is the mineral bauxite. Bauxite is an aluminum oxide. Do you know why aluminum is so special?
Build a lot of
Not just phones. We can build so many things with aluminum. Aluminum is strong metal, but extraordinarily light. It's used in everything from, yes, phones, to your glasses, to the aerospace industry. So much of every rocket or shuttle or rover or anything that's ever gone into space is made out of aluminum. Why? Because not only it's strong, it's light. You have to pay through the nose for every pound, every ounce that you put into space. And so making it out of the lightest metal possible, but still strong enough to get the job done, yeah. Same with airplanes. A lot of an airplane is aluminum. A lot of your bike is aluminum. Yeah.
Like the stuff we put over leftovers as well.
Over what?
Leftovers, like food.
Yeah, aluminum foil, right? You've never really thought about that aluminum foil, but where does aluminum come from, my friends? Do you remember those brown clays, when I showed you the picture of the clear-cut rainforest, the brown clays that were there, that were getting washed into the river? Those are unused clays. The rainforest plants hardly do anything with them. They pretty much just survive after recycling the same ingredients that the generation of plants before them had. The plants rot, the minerals and nutrients go into the ground, the topsoil, and the next generation uses those. No one really puts their roots deep enough to use all the clays. And so those clays just get thicker and thicker and more compact and more compact. And eventually what happens is you make a type of a rock that is rich in those aluminums that clays have in abundance. This. So do you know what that means? Where is the most consistent source of aluminum ore? Underneath rainforests. And because we use aluminum in every part of our everyday life, that is why there is so much money in stripping the rainforests, and why, even though pretty much everyone agrees we shouldn't be doing it, they're going to keep doing it. Now, you can find bauxite deposits underneath where old rainforests used to be. Totally there. Absolutely. But do you think it costs more or less money to try and figure out where old rainforests were, or to go dig where you know a rainforest is right now? Exactly. We haven't developed quite enough as a civilization to be mature enough to say, let's spend a little bit more money on a more responsible course of action. We're not quite there yet. I hope we're not far off, but we're not quite there yet. Okay? Any questions? That's the lecture for today. So are there any questions about anything we've talked about so far? No? Okay. Well, go ahead and keep working on Lab 1 if you still need to finish it. I'm going to pass this box set around. Let's pass it this way. We're going to keep working on Lab. Okay, we've got another hour plus of class time left. So let's do that. Finish Lab 1 if you have not yet. Please try and finish it today. You do have Lab 2 assigned. I am assigning you Lab 3 next time we meet in 2 days. Okay, you're getting Lab 3 sedimentary rocks. All right. I'm going to go ahead and end the recording here.